Okay, so this is assignment 3, and we're going to be talking about drawing electric field lines today. This is a much more conceptual idea. There's not very little math involved with this. But we do need to start with review what our electric field is. And that electric field we determined to be, it's the amount of force that a test charge would experience, amount of force per unit charge that a test charge would experience at anywhere around in this area, in the space around a charged particle. Okay, and so our E is going to equal our force, our electric force, divided by Q0, where this is our test charge. It's the amount of charge on our test charge that is around our more charged particle, and this is in newtons per coulomb. So if we're traveling around in space, if we're moving around in space around our charged particle, we're going to be experiencing some sort of force that's proportional to the charge on our test particle. And so what does this look like, or how would we describe this? So let's try. Let's imagine we have a sphere. Okay, so we have a sphere, and around the sphere there's a distributed positive charge. So we've got a whole bunch of positive charge on the sphere. All right. Close to the sphere, we bring, that's what I'm looking for. Close to the sphere, we bring a test charge. We'll put it right here. Okay, we'll call our test charge Q naught. Okay. What would be a force diagram of the forces acting on this charge? We have all this positive charge right here. The net force on this guy is going to point in what direction? Okay, yeah, it's going to point to the right. It's going to point away. This guy will experience a force as a result of being near this. That's going to point in that direction. Okay. And then what if we put another test charge, and it's a little further away? In fact, let's call it twice as far away. Okay, here's another Q naught. What would the force look like on this? In fact, how long would the arrow be? Half? If it's twice as far away, it would be 1/4 the length of the arrow. I'm not overly concerned with the length of the arrow on this. But if we kept adding a charge along this line, all of these would be experiencing a force that would be in that direction. Yeah? That if we kept the particles traveling along that line, then it would continually experience a force. All of the vectors that would be acting on a particle that's along this line would be pointing in the same direction, right? Directly away from our charged particle. Okay, and so if we put another guy, so we put another one over here, then it would be experiencing a force, in that direction. Or even if we moved one closer, even if we moved one like right here, it would be experiencing a much greater force, but it would still be in the same direction, right? So what an electric field is, it's a diagram of all of the force vectors that an object would experience, that a test charge would experience around your charged particle. So if we had, if we had our charged particles here and here and here, then our force diagrams are going to be out like that, and another one out like that, and then out like that, and out like that. And now, are these the only force lines that we could have. If we put another particle here, we would have another one going radially out in that direction, right? And if we put another one here, it would go radially out that way. So we could conceivably draw an infinite number of force field lines coming out from our charged particle. So when you're drawing these things, what you're going to be expected to do, there will be a problem on your test where you're drawing the field lines around some charged particles. You want to draw enough particles to demonstrate the field space around your charged particle. Okay, so if my 5 lines pointing out from this are sufficient to demonstrate what the field should look like, then you can stop there. A convention is usually 8, is what I've seen. So it's an up, down, left, right. Okay, and then on the corners, on the cardinals, and then on the 45s, are a general way of doing it. But you don't have to, you can do more, you can do less, as long as you're describing the space. Okay. These do not exist in reality. There are no lines coming out of our charged particles. Okay, it's not. They are not distinctly coming out. But the person that came up with this construct, his name is Michael Faraday, who, by the way, he's not quite in the intellectual pantheon. I have my top 3 of Aristotle, Einstein, and Newton. Okay, but Faraday's like next here. He's right there, but he's okay. Oh, that you guys are studying? Okay, yeah. Faraday was pretty studly. And other thing with Faraday is that he was completely untrained. He was a completely self-taught scientist, and because he was not born of noble birth, there was a lot of resistance by the Royal Academy to accepting him and accepting his science, because how could a commoner possibly be as skilled or as intelligent as those that were born of high birth? And when those of high birth started finding out about Faraday and using him as an apprentice and really just erasing his name and putting theirs on top of it to take his work, they realized that Faraday's really got some game, and he really is that good. The word got out, and he started getting some respect. And Faraday is one of the fathers of the field of electromagnetism. He invented the idea of field lines. However, he actually thought that there were actual lines, tendrils coming out of charged particles. There aren't, but it's still an effective demonstration of what a field line is. Okay. Now, there are certain rules that we're going to go over for these field lines. Okay, and we're going to kind of piece them together. One of them is, and so we'll kind of demonstrate that with our next drawing here, is what do you think would happen if we had a negatively charged particle, and near it we bring a positive test charge. Okay. Yeah, the force is going to go towards it'll be an attractive force. And so one of the rules actually happens to be that lines always go from a positive charge to a negative charge. Okay. Now, around the field lines around this negatively charged particle are going to look like something like this. Now, this is sort of begging the question, okay, where are all the positive charges? Right? Because our field lines always go from a positive charge to a negative charge. Here's a negative charge, it's pointing to the negative charge. Where's all the positives? Okay, and this construct, the idea is the universe is electrically neutral. Yeah. Okay, so big thoughts here. The universe is the universe itself is electrically neutral. So somewhere out there, there is a positive charge in that direction that is going to be the initiating point for the field line, and somewhere out this way is a positive charge that is going to be the initiator for this particular field line. And so one of the reasons why the universe is so stable is that it is electrically neutral. If it was electrically, if it was negative or positive, then we would have some funky forces going on, and there would be a concentration of, there would be a mass migration of particles towards one end of the universe over the other. We don't have that. The general force throughout the universe is gravity, because electricity is neutral. So that's one of the rules, that we're going to start at the positive end and move, and we start at the positive charge and move to a negative charge. Okay, so what if we have a dipole? Okay, or what if we have two charged particles, but they have opposite charge? Okay, what happens Okay, so here's one collection of positive. I'll circle it just to avoid confusion. What happens to this guy? Okay, he will experience a force from both charged particles, correct? It will be a repellent force from this one, and it will be an attractive force to this one. And so the field line that he will ride, surfing the field lines, will be that. But what if we deviate? This is sort of the trivial case. What if we deviate from the medium line? What if we deviate from the straight line between them? What would be the force on this guy right here? Well, initially, because he's closer to the positive one, the force it's going to experience is going to be away from here. But at the same time, it's going to be experiencing attractive force towards this. Okay, well, I'm going to try and... Okay, so he would have one direction like that, and then he'd have another direction there, right? So imagine how those vector sums would be as it moves around, and you start getting something like that. Okay, and no, it is not, because no, it's not just a straight line. Because if he's below, if both of these are below, he's initially pushed out in this direction, and he'll get pulled in, but it's not a parabola because of the squared in the of the distance. So if we put a guy down here, we get the same things down here. And we'd get a medium in here, and we have another medium one in here. Let's say we put a guy over here. All right. Now, why wouldn't he go straight back towards the negative? He has to avoid this one. He's much closer to the positively charged one, so he has to avoid it before the effect of the other one comes into play. So this will actually swoop out and then eventually make his way back, and this should have been out here a little bit more. But this is where field lines go. And so we start getting these field lines. Okay, and we'd have the same thing over the top, except I'm just running out of paper, so I can't draw them up at the top. But this makes sense to you guys? Okay. Nick.
What if it's directly on the left side or the right side?
That's a good question. If it is exactly opposed, this would be shielded by that. I'm sorry, this would be shielded. So if our test charge is here, right? The force of this one is shielded by the force of that one, and it would continue on. It would continue on. It would have a force in the positive direction. It would be decreasing in. I'm sorry, to the left. However, it would be an exceedingly unstable equilibrium. And so if at any moment it fell off of the mathematical line between the center points of the two charges, it would veer off and come back around. Okay, so it has to be exactly on the line for it to be able to continue on straight. If it veers, then it swoops back. Okay? Is that okay? Right. Okay. So that's with the positive and negative. So another rule is you have to draw arrows. By the way, you have to show the direction from the positive to the negative part of the field. Thou shalt draw arrows. If you do not draw arrows, you will forfeit 2 points of your exam score. Okay? They disappear. Right? Gone. Now, you have to draw arrows. Another thing, equal charges have equal number of field lines coming out. So, let's redraw this. So if we have let's say this is a 4 microcoulomb charge here, and we have an 8, negative 8 microcoulomb charge here. Okay, we're going to experience a couple things. One is that our forces, along the line is the trivial case. It will go straight there. But as we push away, okay, the stronger force takes over, and so we have less loopy turns. So we have something coming out here. It's going to swoop in. You guys following that? Okay. However, I've got 5 arrows coming out of this one, right? You guys following me here? But this is twice the charge. So I need twice the number of arrows coming in towards this one because it has twice the charge. Now, the number of arrows that you draw, the number of lines that you draw is arbitrary. You can choose whatever it takes to show your field. The proportion between your between your charges is not arbitrary. If I draw 12 lines coming out of this guy, I have to draw 24 lines coming out of this guy, or going into this one. That makes sense? Okay, so the field lines are proportional to the amount of charge. Okay, last one. You will never, in fact, I'm not even going to draw it on here. Well, I don't want you guys to draw it in your notes. Okay, in fact, I will erase it. I don't have one ready, unfortunately. Shoot. You will not see this. Okay? 2 field lines shall never, ever cross. It leads to total protonic reversal and all of your atoms will explode at the speed of light. And you guys don't know what I'm referring to, do you? Ghostbusters? You guys ever seen Ghostbusters? If you haven't seen Ghostbusters, you have to see Ghostbusters. It is hilariously funny. That being said, you don't cross the streams. Okay, we don't cross the streams because when you cross the streams, it leads to total protonic reversal and all of your atoms explode at the speed of light. That's okay. Well, yes. That kind of goes along with all of your atoms exploding at the speed of light. Okay. But more technically, think about what happens here. How did we come up with these lines? These lines are a representation of the direction of the force that a particle would experience at any particular point in space. So, if we have a particle right here, that means it is experiencing a force in that direction and in that direction at the same time, and these lines represent the net force on a particle. Is it possible to have two different net forces acting on a particle? No, there can be only one. Another movie reference. Go check out Highlander. Okay. Now, so we don't cross the stream. So what are the rules? We're going to quantify the rules here. Rule number 1. Rule number 1. We start at the positive. End at the negative. Rule number 2. Okay, the number of lines is proportional to amount of charge. The number of field lines is proportional to the amount of charge. All right, and the mutual proportions, they can be arbitrary. Number 3. Field lines try to fill okay, so draw field lines to try to fill the space. To fill the space, not feel the space. Field lines try to fill the space, and for never never cross field lines when you're drawing. Ever. Ever, ever. In fact, this might even be number 1. This is the overarching principle. Do not cross field lines. That is an automatic on your problem. In fact, I will, if I see a crossed field line, you get no credit for that problem, for the field line drawing. You do not cross field lines. Okay, so we're going to practice this a little bit. Okay, what's that going to look like? What would the field lines be between a negative 5 microcoulomb charge and a negative 3 microcoulomb charge?
From outside. Right? From the outside.
Draw it. Draw it. This is, you guys practice. Draw this. The test charge helps you determine the force at any particular point in the electric field. What you are drawing is the lines that like the continuous like over here. I put a test charge here and here and here and here and here and here, and that's how I determined that would be the field line. So it's the continuous.
What's
What's that? Okay, that's the first one. The other one, so there's two practices. One is this, the other one is you have a okay, so you have two different situations here. You have negative 5 microcoulombs, negative 3 microcoulombs, then 3 microcoulomb, 3 microcoulomb, negative 6 microcoulomb. These three. Okay, and that is the end of this lecture.